Okay, so hi everybody, welcome to another pre-recorded lecture. And so, yeah, actually, I originally intended pre-recorded lectures to kind of be maybe cover some background, which some people know and some don't, so you can kind of skip ahead. And this is one of those lectures where it fits perfectly. Like, I'm going to explain root systems, and then some of you know a lot about them, and so in which case most of this material is going to be familiar to you. But if this is new to you, then I'll try to explain some of the aspects, but then of course it's not going to be comprehensive at all. The root systems is a pretty big subject. There's whole books written on those things. And so yeah, so last time I was talking about cluster algebras of finite type. And so I asked the question, like, how do you classify all of them? How do you find, like, for an example, if you take the path quiver Q, gives you a cluster algebra of finite type. Okay, is there more than that? Do other quivers exist that give you finite type? Like, it's a good game. You can take a quiver, you can start playing with it, and kind of see if you get finitely many seeds or infinitely many seeds. And so it's not clear how to do it in general, and I'm going to do something that is perhaps unexpected. I'm going to completely forget about cluster algebras for a while, and instead I'm going to just explain root systems, which is some other kind of it looks completely unrelated, but in the end it's all going to be related, so keep that in mind. Alright, let me start. I guess one thing I didn't mention last time, which I was going to mention, is that now is a good point to kind of give you an overview of the rest of the class. I don't mean this lecture, but just all future lectures are going to be roughly divided into two parts. So, plan of the class. And so the two parts are going to be, first of all, the first part is going to be about periodicity of cluster algebras and finite types and stuff like that. So it's going to include root systems, Coxeter groups, and then using this to classify cluster algebras of finite type, and also kind of more general periodicity phenomena. And yeah, let me also write integrability. If you were present in the last lecture, there was Fibonacci numbers showing up, and they satisfy linear recurrence, and that's not that's also that can be made in the general phenomena. There is a kind of periodicity is like finite type, and then these linear recurrences are like affine type. So I'm going to explain that as well, and that's the first part. So and then I'm going to switch, and in the second part I'm going to discuss these positroid varieties. For example, this pi circ kn. So this is going to be about the Grassmannian cluster algebras. And so I'm going to discuss their relations to cluster algebras, and so they are cluster algebras and the corresponding QT Catalan, the relations to the to these mysterious QT Catalan numbers, and also the knot theory. And so let me mention that kind of these two, well, a lot of these things are subjects of pretty recent research. So there's a lot of exciting things going on right now, and I'm going to try to cover some of those things. Well, there's going to be a lot of open questions there as well. And so, yeah, let me now just proceed to explaining root systems. And so I'm going to start with reflection groups, which is kind of a precursor to root systems. And it's, okay, so it's going to be, as I said, completely non-obvious why this is supposed to be related to cluster algebras, and it's actually it's a notion that's much older than cluster algebras, but it's a very natural notion. So what do you do? What is a reflection group? Well, so you start with so let B be a finite dimensional vector space. So just some r to the n. And so for a vector alpha inside this space, I'm gonna denote as alpha denotes is the orthogonal reflection with respect to the, so is the corresponding reflection. And so what it does is, so okay, let's say I denote by h alpha the hyperplane orthogonal to alpha. So it's the set of all vectors v inside v such that the usual dot product, well, okay, let's say I fix some scalar product on v, and then so the hyperplane orthogonal to alpha is just defined like this, and then as alpha sends alpha to minus alpha, and then alpha preserves all points of the hyperplane. Points of h alpha. So that's exactly like a reflection. So you have a picture like this. That's your h alpha, and then here's the origin, and then this is alpha, and so as alpha acts as the identity on h alpha, and then it reflects like this, negative alpha. And so here's a question. How do you write what is a formula for S alpha? So let's say you have some vector v, v in v. What is S alpha of v? Or should it be beta? Yeah, let's say instead of v I'm going to write beta. And so, well, this is easier to do when alpha has norm 1. If alpha has norm 1, then so here's your hyperplane, here's alpha, a unit vector, and then here's some other vector beta. And so you want to reflect it to get this new vector as alpha of beta. And the way you do that is you add some multiple of alpha to this vector, and that multiple of alpha should be twice the like if you project beta onto the line through alpha, then you're supposed to add twice as much. So if alpha has norm 1, then the S alpha of beta it's not hard to see that it's given by beta minus the projection, which is just the dot product alpha of beta on the alpha times beta, sorry, times alpha. Right, so you shift in the direction of alpha by this much. Okay, But in general, if I multiply alpha by some constant, then this coefficient has to be divided by, there is a 2 here, right? Yeah, twice this amount. And so, in general, if I multiply alpha by some number, but like if I increase alpha by 7, then this coefficient should decrease by 7. And so, so the actual formula is, let me write it down, it's, yeah, I just have to renormalize by the norm of alpha, by the squared norm of alpha. Alpha comma beta divided by alpha dot product with itself times alpha. So if I multiply alpha by 7, then this, you're going to be divided by 49, so, and then this is going to be multiplied by 7, so the coefficient is going to be divided by 7. All right, and so so that is the formula for reflection orthogonal to a vector alpha. And so now let me define, so first of all let me note by O of V the isometry group, well, it's called the orthogonal group, just the group of all isometries that preserve the origin. It doesn't really matter what it is, but what I'm going to define next is the, so a reflection group by definition is a subgroup of O of V, which is generated by reflections. Okay, so you pick some collection of reflections, and then you apply them in all possible ways, and you get possibly finitely or infinitely many isometries of your space. Isometries, it preserves the scalar product. And so, okay, so the question that I'm going to ask here is how to find finite reflection groups. Yeah, let me give you an example of a finite reflection group. You can try to think of an example right now by pausing the video. But yeah, a good example is the dihedral group, which is, so you choose, you draw like a regular 2n gun. That's not really regular, but okay. So here's the origin, and then you just take all hyperplanes through the, well, all lines through the vertices. And so these are your hyperplanes, like H1, H2, H3, and H4. And so it is easy to see that if you, well, it's easy to see that these reflections, they, well, it's enough to take only two lines instead of 4. And as you keep applying these reflections, you get basically the symmetry group of this regular. So you take a regular 2n gun, and then you get the dihedral group, which is the group of symmetries of that 2n gun, and it's known to be finite. So, well, yeah, I guess you can also include like the reflections across the midpoints of the sides. But anyway, either way, it's a finite reflection group. And so, okay, is that it? Is there any more? Like in a three-dimensional space, is there a non-trivial configuration of planes such that it generates a finite reflection group? So that's a non-trivial question. And so Now let me, instead of thinking about these hyperplanes, let me instead think of the vectors that are these alpha vectors, which are orthogonal to them. Somehow it's going to be easier to think not in terms of hyperplanes, but in terms of the vectors. So, and that is called root systems. Root systems. Okay, so what is a root system? Here's a definition. Just right away, I'm going to give you the definition of a root system, and then we're going to try to understand its properties somehow. And so, by the way, different people mean different things about root systems. There is an important axiom which is not included in this list, but I'm going to introduce it later, the crystallographic root system. But so far, let me say that a root system phi is a subset of V such that it has to satisfy these three axioms. So the first one is that for any line contains at most two elements of phi. So if you choose a vector of phi and draw a line through it for any alpha in phi, the span of alpha intersect phi is equal to plus or minus alpha. So it's closed with respect to negation, and there is no, the only multiple of alpha that belongs to phi is negative alpha. Now the second axiom is that, well, that's actually an interesting one. So for any two vectors alpha and beta inside phi, you get that the reflection of beta with respect to the hyperplane orthogonal to alpha belongs to phi. So phi is closed under reflections generated by the vectors of phi. So yeah, these root systems are supposed to be highly symmetric objects. So you can think about, even though it's not really clear from these axioms, but they're going to have very, very large symmetry group, each root system. And so finally, the last axiom is that phi is finite. And so if it satisfies these three axioms, then it's a root system. And so let me also right away mention an important root system. So that's the most important example of a root system that you will ever find. And so it's called the root system of type AN, or yeah, I usually am going to prefer to write AN-1. And so the kind of the explicit description is that first of all, V is just the set of all let's say elements V inside R to the N, such that the sum of their coordinates is equal to 0. Sum from 1 to n, Vi is equal to 0. I'm just taking the hyperplane, so V is an n-1 dimensional space. And so the roots phi consists of all just differences ei minus ej, where I is not equal to j, and they are both between 1 and n. And here these ei are basis vectors in R to the n. Right, so ei is like 0, 0, 0, 1, 0, 0, 0, 0, where 1 is in the ith position. Okay, and so I have given you a collection of vectors. Why is it a root system? I have to check these axioms. and which ones are clear. So I guess C is clear, right? Phi is clearly a finite set. Now, what about A? I guess A should also be clear, right? Because if alpha is EI minus EJ, then negative alpha is EJ minus EI. So both of these are included in the set, and none other multiples of alpha are included. So that's also check. But then the only non-trivial one is B, right? I have to check that for all alpha and beta I have this property. And so let's say, so I want to check B. So let's say alpha is equal to EI minus EJ for some I not equal to J. And then I want to compute S alpha of some other vector. Well, let's say even not just some arbitrary, yeah, let's say beta, okay. Beta, where beta is just some vector beta 1 up to beta n, even in R to the n. So how do I reflect beta? And then, so we have a formula here. So what's the formula? Beta minus twice the ratio of two dot products, alpha comma beta divided by alpha comma alpha times alpha. And so alpha dot product with beta is what? You take EI minus EJ times this guy, so it's just beta I minus beta J. And now alpha comma alpha is, you multiply this vector, it has length square root of 2, so its dot product with itself is the squared length, so it's equal to 2, and therefore these two, kind of the 2 in the denominator cancels out with the 2 in the numerator, and what you get is beta minus twice, well, sorry, the 2 cancels out, beta minus the dot product of alpha and beta, so beta I minus beta J times alpha, which is EI minus EJ. And so, okay, so I'm going to get a vector. So if beta is equal to beta 1, blah, 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 beta I, etc., beta J, then for S alpha of beta, what I'm going to have is clearly, like, I'm only adding EI and EJ, so the other coordinates are not going to change. And so beta 1, etc. And instead of beta I, what do I get? Beta I. So instead of beta I get beta I, which comes from here, minus beta I minus beta J times EI, right? Which is, I mean, the beta I is just gonna change by this amount, and this is the same as beta J. So instead of beta I, I'm gonna get beta J, and similarly, beta J is gonna be replaced by beta J minus beta I minus beta J times EJ here, right? And so so here I'm going to have a minus EJ, and so this sign is going to become a plus, and therefore I'm going to get beta I. So the effect of a reflection with respect to S alpha is just that I have swapped these two values. So that's an important rule to remember. So for alpha equal to EI minus EJ, the effect on any other vector is you just swap the two entries corresponding to I and j. And so in particular, if you look at these vectors phi, right, so if beta belongs to phi, then beta is just some ea minus eb for some a not equal to b. And so the point is that it has like coordinates 0, 0, 0, plus 1, 0, 0, 0, negative 1, 0, 0, 0, 0 at spots a and b. And so no matter how much you permute pairs of coordinates, you're still going to get a vector of this form. So, and therefore axiom B is true, right? So, yes, alpha of beta is also of this form. And therefore B is true. And therefore phi is a root system. Yes. So this type A n-1, that's the single most important root system. So please remember at least the definition. The definition is very simple, right? You just ei minus ej, that's it. Now, I guess I also need to explain how do you go between back and forth between root systems and reflection groups. And the idea is pretty straightforward. So if you let's say you have a root system. So if phi is a root system, then I'm going to define W sub phi is just the set of all, well, it's the group generated by all reflections, where alpha is a vector in phi. And the angle brackets here mean, so yeah, it's generated by S alpha. Just take all these reflections orthogonal to alpha. And similarly, if W is a finite reflection group, then I can look at all reflections in so I get a bunch of hyperplanes, and then for each hyperplane I'm going to choose the two unit vectors which are orthogonal to that hyperplane. So phi sub W is the set of all alpha in V, such that alpha has length 1 and the corresponding reflection belongs to W. And so clearly, if it's a finite reflection group, then clearly this is a set of finite size. But it's less clear that if I take a root system, then what I'm going to get is the corresponding reflections generate a finite group. But it's true, right? So and so, yeah, I guess lemma is that W sub phi is a finite reflection group, and phi sub W is a root system. And so the proof is it's not hard. So I'm going to leave it as an exercise. But I'm going to give you, so the kind of the main idea here is that main idea is like, why do this condition that S alpha of beta belongs to phi is a little bit weird. Like, how is this related to reflection groups? And the answer is that the answer is conjugation. So if you have an element t in the, if you just have any isometry, right, and then you have some vector, some non-zero vector alpha, then if you take the reflection corresponding to alpha and then you conjugate by t, conjugate this reflection by t, then what happens is you get another reflection s t alpha. Right. So if t is some kind of rotation or whatever, then conjugating s alpha by t corresponds to this kind of like a basis change. So you rotate and then you reflect and then you rotate back, which corresponds to reflecting across the rotated vector, something like that. So that's basically the proof of this. I mean, it's not quite a bijection, right? Because in a root system, the length of the roots can be arbitrary. And if you take a finite reflection group, then you get a root system where all root lengths are 1. And there is further issues, like if you, I mean, if you consider these groups up to isomorphism, and then there's kind of, you have to define a notion of isomorphism for root systems, and it's, I'm not even gonna go into this, but the point is that once you have a root system, you're gonna have the corresponding reflection group is finite. And once you have a finite reflection group, then the corresponding unit vectors form a root system. And so now here's a question. So let's say I take my favorite example, which is the root system of type an-1. And so if phi is of type an an-1, question what is w sub phi? So it's defined up here. No, up here. I'm just taking all these reflections with respect to S alpha, where alpha is, so alpha is like EI minus EJ. And then, as we discussed, the corresponding reflection just swaps the values, swaps the ith and jth coordinates of the vectors. And so, and then I take the group generated by all possible reflections like this. All possible transpositions of pairs of entries. So what is this group? And as you have probably guessed, the answer is W sub phi is a symmetric group. Symmetric group. The group of permutations of these n coordinates. Okay. And so, so that's basically, I mean, yeah, I guess one thing I need to say is, well, all I want to say is that if you want to study finite reflection groups, then it's the same thing as you want to classify like finite roots, classify root systems basically. And where you don't care about the length of the vectors. But for us, the lengths are going to be important. So I don't want to fix them all to be 1. There's going to be more interesting stuff where I need vectors of different lengths. And so I guess, yeah, one thing I want to mention is that if you want to classify root systems, then you only want to look at irreducible ones. So by an irreducible root system, I mean definition. A root system is called reducible if it's like a direct sum. It's an orthogonal sum of 2 root systems. It's easy to see that if you take 2 root systems and put them in the orthogonal subspaces, then the result is still going to satisfy all these properties. And so a helicopter flying by. Okay, phi is reducible if it can be written as a disjoint union. Phi the union of phi1 square cup phi2. So square cup means disjoint union phi2, so that alpha 1 is orthogonal to alpha 2 for all alpha 1 in phi 1, alpha 2 in phi 2. And so I'm only going to be interested, I'm usually going to be interested in irreducible root systems, satisfying this other minor condition that the span of my root system is the whole space V. If it's not the whole space, then I just replace V with the span of my root system. Like here, for example, I took V to be the hyperplane where all the sum of coordinates is 0. That's because that's the span of all these vectors, rather than taking the ambient space R to the n. Okay, and so now root systems have very nice structure, and so I'm gonna, usually people study them. There is a very interesting, you can, instead of looking at all the roots, you can look at a certain kind of minimal set of generators. These are called simple roots. And like, what is this? What are simple roots? So you fix, let's say phi is a root system. And here are the axioms again. And then, so here's a definition. A simple system, delta, is, well, it's a subset of roots. So delta is a certain particular set of roots, is a subset such as satisfying the following properties. So the property is that for every, well, basically the property is that every root is either positive or negative. For every alpha in phi, we have either alpha belongs to the non-negative span of the elements of delta. So alpha can be written as a alpha, so if delta is like alpha 1, alpha n, then this means that alpha, well, this means that alpha can be written as the sum of Ci alpha I, where all Ci are non-negative. And so the claim is that we have either, well, every root system has alpha and negative alpha, so if alpha is a non-negative linear combination of elements of delta, then minus alpha is going to be a non-positive. So we have, for every alpha, we have either that alpha is a non-negative combination or that alpha is a non-positive combination of the elements of delta. And I should also say that delta is not just a subset, but it is a basis of our space V, satisfying this extra property. And so it's really not clear, like this is a pretty strong requirement. Usually when you have a basis and you have a vector, then some elements have positive coefficients and some coordinates are positive and some are negative. But somehow here I'm asking for a basis such that any root has either all positive coordinates or all negative coordinates. Okay, so let me show you an example. Let me actually draw. So let's say I'm going to take the root system of type A2. So A2, the special case of a n minus 1, where n is equal to 2, n is equal to 3. And so what do? I take the three-dimensional space, and then I take the plane where the sum of coordinates is 0. So it's going to be a plane, and it's a two-dimensional space. And so it looks kind of like this. And well, and let me now draw the roots in the plane. So there is going to be, well, basically the roots are going to be the vertices of the hexagon, of a regular hexagon. That's not regular. Okay. So that's the origin, and then so I'm drawing the plane where in the three-dimensional space where the sum of coordinates is 0, and then I have this E1 minus E2, and then this is, let's say, E2 minus E3, and then this guy is the sum of these two vectors, so that's E1 minus E3, and then I also have the negatives. Yeah, let me erase, this is not helpful. So then I also have the negatives. Yeah, E3 minus E2, E3 minus E1, and then E2 minus E1. So they all live in the plane. They are all orthogonal to the vector, 1, 1, 1. And so, question now: is there a simple system inside of this root system? So I'm supposed to choose a basis of V. V is a two-dimensional plane, so I need to choose two elements such that all the other ones are a positive or a negative combination. And indeed, if you choose, let's say, this guy here, and you call it alpha 1, and then you choose this guy here, and you call it alpha 2, then you can see that, yeah, let me actually erase. So instead of E1 minus E3, I'm just going to write alpha 1 plus alpha 2. And you see that both coefficients are positive. And then all of these guys are going to be just negatives of that. Let me even erase this. So negative alpha 2, and then negative alpha 1, and then this is going to be negative alpha 1, negative alpha 2. So I could have chosen any pair of roots which are 120 degrees apart, and then that would give me a simple system. And you can check that if, for example, I choose this guy as alpha 1 and this guy as alpha 2, and then the third guy is going to be their difference. So, and having the difference is not allowed in this definition. So, okay. And in general, so yeah, let me write down alpha 1, alpha 2. If this is delta, then this is a simple system. And so the elements of delta are called simple roots. So in this case, alpha 1 and alpha 2 are simple roots. They always form a basis, and they have this nice property. And yeah, so in general, in general for type a n minus 1, you can try to guess what are the simple roots, and one possible choice is you can take delta to consist of. So I should choose n minus 1 vectors. And a natural choice is to have E1 minus E2, E2 minus E3, etc. en minus 1 minus en. So then with this choice, if you have, so for I less than j, ei minus ej is, so if, let me denote these roots by, let's say this is alpha 1, alpha 2, all the way up to alpha n minus 1, then ei minus ej, if I is less than j, and this is just alpha I plus etc. plus alpha I plus 1, all the way up to alpha j minus 1. And if I is, and so if I is less than j, I is less than j, but I take ej minus ei, then it's going to be minus this, minus alpha I plus etc. plus alpha j minus 1. And so you see all coefficients have the same sign for any root of my root system. And so, as I said, it's non-trivial to see whether simple roots always exist. I give you an abstract root system, how do you find these elements? But it's actually not too hard, like you kind of choose like a generic hyperplane, and then you look at the roots which are somehow closest to that hyperplane. Yeah, that's not really a proof, but it can be completed to a proof. And so yeah, let me just state the properties of these simple roots. Well, I guess I need to say another, introduce another notion. So if I have chosen the set of simple roots, then that gives me it represents phi as a disjoint union of positive roots and negative roots. So positive roots are the ones, so alpha in phi, such that alpha belongs to R. It's a positive combination of elements of delta. And also I'm going to have negative roots. Here alpha is in phi, such that alpha is a negative combination of delta. And so, and let me introduce notation. This is going to be positive roots. The set of positive roots is denoted phi plus, and then the set of negative roots is denoted phi minus. And so phi is a disjoint union of phi plus and phi minus. And so now the lemma is that root systems have very nice structure. So this definition, even though it sounds ambitious, right? I want some strong properties. Even though that is true, still I get, first of all, they exist. Okay, so let me write it down. Let phi be any root system. Then the following is true. So the first property is that phi has at least one simple system. So surprisingly, you can always choose these simple roots. And then the second property is that the corresponding, so remember W sub phi is generated by reflections orthogonal to these roots. And so it acts on, well, it acts on these simple systems simply transitively. On simple systems. I guess that's a lot of simple, but yeah, let me kind of just remind you that simply transitively means that for any two simple systems, let's say delta and delta prime of phi, there exists a unique element of W sub phi. let's say element, let me denote it by, I don't know, u in w sub phi, such that u takes delta to delta prime. So that's, again, that's a very strong statement. It not for any two simple systems, there exists a unique element. So in other words, somehow this, and remember, like w phi is generated by reflections, but you get many more. Like if you look here, you can apply s alpha 1 and then s alpha 2. Oops, sorry. You can apply s alpha 1 and then apply s alpha 2, and what you're going to get is some rotation. And rotation is not reflection. So there are many more things, but somehow the elements of w sub phi are in bijection with simple systems. So again, that's very kind of rigid structure. And finally, the third property is that you can, so every root alpha in phi appears in some root system. Sorry, in some simple system. Just as here I could choose any root, any given root participated in a simple system. And so this lemma, it kind of justifies my claim that root systems are very highly symmetric objects. All simple systems are pretty much the same, like are connected by these multiplication by these elements of the corresponding reflection group, and then every root appears. So in a sense, all these roots are just created equal. And I guess that's basically all I want to say today. I think I'm out of time, and so homework is due on Wednesday. Depending on when you're watching this, it may be very soon. And I guess that's it. So thank you very much.